All right, so that's done being yelled at. So here's what I want to talk about today. We're going to talk about an inclined plane. Now, before I go into it too much, can anybody name one of the four simple machines? You know, middle school. Go ahead. Inclined plane is one, or the wedge is what it probably would have been called in middle school. What's another one? There's four. Really? Nobody? Everybody looking down? That's not good. Was middle school that terrible a time in your life? You don't remember any of it? All right, first period got them all. So I'm a little frustrated. Go ahead. What's that? Pulley's one, that's right. So we got wedge, pulley. There's two more. Lever, very good. One more. Nope.
A gear.
A gear. Well, we call that a wheel and axle, but I'll go with gear. That's good. At least we got somebody from home, a couple people in the class, but those are the four simple machines: wheel and axle, pulley, inclined plane, and lever. Now, I want you to know those four because all four of them come up. We're going to talk about the inclined plane right now, but those are the four simple machines. They all do the same thing. They exchange force for distance. I'm waiting patiently. I don't like to repeat myself a lot today. You guys have been in my class long enough to know there's a pause. That's something that's written down. They all exchange force for distance. What that means is you can use them to either apply more force, but you won't be able to do it over a very long distance, or they allow you to apply less force, but you'll have to do it over a bigger distance. For example, all of you used a wedge today because you had to use a wedge to get up to my classroom. You probably called it stairs, but it's a wedge because most of you can't just jump to the second floor. You make little jumps instead. Smaller applications of force, but over a longer distance. That's what a wedge is, a ramp. It allows you to apply less force, but you will have to go a longer way because you're applying less force. You want to be able to open the door later. Most of you just can't wait to leave physics. Well, luckily there's a lever over there. That lever allows you to apply more force at the center than at the edge. The center doesn't move very much. The edge moves a lot. More force at the center, smaller distance. Less force at the edge, longer distance. All simple machines exchange force for distance. Now, we're going to talk specifically about the wedge or the inclined plane. And there are several features of the inclined plane that I need you to know. It's worth me saying this in a way, I don't like to say it like this, but some of you will just have to memorize this, and you've got until Friday to get it memorized. Some of you can figure it out. And for those of you who can figure it out, don't worry about memorizing it. I don't need you to memorize it. But for those of you who you're just not good at the trig and you don't have the geometry skills and you can't name the simple machines because that was middle school, you guys should probably look at memorizing. So I've placed a box on my inclined plane. What I would like you to do is off to the side. I want you to consider what forces are acting on the box, assuming it's staying in place right there. Jot yourself down a couple of arrows. All right, my suspicions are you have drawn 3 arrows. First one, pretty easy, I hope. The weight of my box straight down. Labeled, I don't know, weight or mg. I tend to just write mg once we get rolling. I don't write weight most of the time. Now, the next couple of forces shouldn't have been too tough, but if yours are wrong, you'll need to correct this. Is the box in contact with anything? So there should be a normal force. How did you draw the normal force? I hope you drew it perpendicular to the surface. Which means it should be drawn upward and to the left. Every year I get a test with an inclined plane problem. Somebody draws a normal force straight up every year. Don't let it be you, because I'll put it on that. I'll put it on my bulletin board. Okay, I don't want this to be you. On an inclined plane, the normal force has to be perpendicular to the surface, which is at an angle. And I have students who do the same kind of thing with friction. They draw it to the right, but it's not to the right. Friction has to be perpendicular to the normal force and has to be parallel to the surface. So in this case, friction probably acts in this direction to keep the box from slipping. And yes, I think friction should be drawn smaller than a normal force, but it should be clear that this is a right angle. These are the forces of an inclined plane, and this assumes that there's a frictional force because the box is at rest. Something had to hold it in place. If there was no friction, then it would slide down the ramp. The friction is keeping it in place. But if I want to analyze this question, the next step would be to draw in a coordinate system that would support the analysis of this problem. Now, how would you draw that coordinate system? I think that's a good call. I'll remind you, we have 3 priorities. Priority number 1 is to draw it in the direction of the acceleration. Now, this box isn't accelerating, but if it were going to accelerate, it would likely accelerate down the ramp. But it's not. Next would be to draw it in a direction that's moving. It's not moving. But if it were moving, it would be either up or down the ramp. And the last one is to draw it in such a way that it's aligned with as many forces as possible. Well, that's clear that to align it with as many forces as possible is to align it with the normal force and the frictional force. So I would expect you to have a coordinate system set up like so. There. And have labeled perhaps positive X, maybe positive Y. Now, here's the hard part, or at least hard for some students. Inclined planes are usually defined by their angle of inclination, which my big head is covering. So there, angle of inclination. Where does this angle go in my picture? Meaning, where do I put it in my free body diagram? Some of you can figure this out without needing my help, and some of you can't. So let me just be very clear, and you should have this in your notes. This requires memorization because this is the part that people screw up. Find the axis that goes through the normal force. The angle goes between the weight and that axis. We're going to do an activity on this, but not necessarily before Friday. We're going to do an inclined plane lab. Now, in saying this, I can prove this to you, but I can't prove it to everyone because some of you don't remember enough of your geometry. To prove it to you, I'm going to draw 2 lines on my original diagram. One that's perpendicular to the incline, and one that's perpendicular to the floor. Now, if you remember anything about geometry, you know that there are 3 similar triangles drawn right there. There's 3 of them. There's the big one that's here. That's one triangle. There's the slightly smaller triangle. And there's a little bitty triangle. They're all similar. And because they're similar, we know that this angle and this angle have to be congruent. And this angle and this angle have to be congruent because they're similar triangles, and that's why that's theta. And that's why it goes there. Look, write the sentence in your notes. The angle of the incline appears between the y-axis and the weight. Get that right, please, because everything hinges on it. Consider that we're going to have two components, right? I'm going to wrap a triangle around the angle. If you've labeled the angle wrong, everything from this point forward is also wrong. When I wrap that angle around the triangle, with my right angle being right there, this side has to be mg cosine theta, and it represents the force into the ramp. It tells us how much normal force we're going to have. And then there's mg sine theta. It represents the component that pulls the object down the ramp. It is this component that determines how fast the object is pulled down the ramp. It's this component that generates the normal force, which of course that means it generates the frictional force. For all ramps, we're going to have two important components: the component that goes down the ramp and the component that goes into the ramp. If the geometry bothers you, then commit that to memory, that these are the two components. Sine goes down the ramp, cosine goes into the ramp. If it helps you, sine is the function that gets bigger when the angle gets bigger. So a steeper incline is going to have things slide down them faster. That's because the sine is getting bigger with the angle. Means more force is down the ramp. Now you should have a big picture of this in your notes. You should study that. Commit pieces of it to memory. We don't have time today to do an example with an incline plane, but they're in your homework. So I would encourage you to finish up the homework and practice with the incline plane. Tanner? For this problem, yes. Tanner said right now, because it's not moving, we would say that in the x direction, the net force is 0, so mg sine theta would equal the friction force. That would be true in this problem. And same for the y direction, that the normal force would equal mg cosine theta. For most inclined plane problems, this will usually be true. We usually don't see objects sinking into our ramps or flying off our ramps. But this is not always true. Our objects are usually going to be accelerating down the ramp. They slide down the ramp, things like that. We use ramps. So you should expect our questions that have to have ramps in them will have the boxes moving up or down the ramps. All right. That's going to be it for today, because I'm expecting them to interrupt us for announcements. And so are there any questions about what's happening over the next 2 days? Tomorrow, we'll spend the first few minutes talking about problems like this. I'd say 10. Then the rest of the class is going to be dedicated to reviewing for your test. Let me tell you what your test is right now. 2 force problems. One of them will be an inclined plane question, and one of them won't be. And a collection of multiple choice questions. Probably between 5 and 7, maybe 10 multiple choice questions. That's the test on Friday. There are 2 versions of it. This afternoon, I will post a practice test. I encourage you to look at it. If you did the problems last night for homework with no difficulty, you are very likely going to be in good shape for the test. All right? Any questions before I release you guys? Well, if I let the people at home out soon, they won't know what for lunch is happening today. I know that that's going to be terribly disappointing, but I think that's it, guys. The bell's going to ring in about 3 minutes. You guys at home, you're welcome to enjoy these 3 minutes. Maybe use the restroom or go fix yourself breakfast, or I don't know, but whatever you would do in 3 minutes. They have to just sit here in the classroom. It's probably not going to be as much fun. So bye-bye, folks. Have a good day.